Now that we have the idea of the fundamental theorem of calculus behind us and our power rule for integration, let's go ahead and look at some other ways that we can apply integration. First thing we want to start with are talking about even and odd functions. Now you may have been exposed to even and odd functions before in an algebra class, so some of this may be familiar to you. An even function has a particular characteristic of plugging in your values for x and negative x into the function. So if a function is even, that means the original function is equal to the function evaluated at a negative x. So we'll show you a quick example here. This is a really nice little simple even function. This is the quadratic equation y equal x squared. So this is f of x equals x squared. Now note, if we plug negative x in here, this would be negative x quantity squared. When you square a negative, of course, you get a positive, and you can see f of x and f of negative x are the same, so this is an even function. Well, one of the characteristics that we can talk about with an even function then is that the integral, let's say on this particular one, let's go from negative 2 to positive 2. So the integral from negative 2 to positive 2 of this x squared dx, that would be the same as finding half of the area. It's usually easier to find the side that's positive, and then doubling it. So we would go the integral from 0 to 2 of x squared dx, and then I would double it because it's symmetric. The area on the right is equal to the area on the left. So these are equal areas. So this is a way that we can rewrite an even function to simplify finding the integral. Now if you didn't want to use this property, you wouldn't have to. You could integrate this directly and still get the same solution. So in general, if we have an even function and I'm integrating from negative a to positive a of f of x dx, that's the same as doubling the area from 0 to a of f of x dx. Now you don't have to use this. Sometimes it comes in handy though, and it's a nice characteristic to know about when you're working, because sometimes it can make this a lot simpler to integrate from 0 to 2 than from a negative to a positive value. A lot of people run into problems when they have evaluating negative values, and so again this just kind of tries to clear that up. Okay, let's go ahead and look at an odd function. And again, with an odd function it has a particular algebraic characteristic, and for an odd function that would be f of negative x is equal to the negative of f of x. So let's go ahead and look at a quick picture, and then we'll try and explain what happens here. Actually, you'll see what happens here as soon as we try and integrate this. And I'm going to choose some pretty simple functions. Let's look at this function. This is the function f of x equals x cubed. Okay, so now let's look at f of negative x. This would be a negative x quantity cubed. Negative to the third power is negative. Negative f of x would be the negative of our x cubed, and you can see that these are equal, so that tells me that this is an odd function. Well, if I'm looking at this, let's say from negative 2 to positive 2, I can see that the area on the left and the area on the right are the same. However, one is below the x-axis and one is above the x-axis. So what that's telling me then is they would cancel each other out. So whatever area this is, and we can find that out, and whatever area this is, this would be the negative of that area. And so the sum of these would be 0. So our net area would be 0. So if you want to look at an odd function from negative a to a of f of x dx, what ends up happening is the area ends up canceling each other out above and below, and the net area is 0. So these are kind of our quick little shortcut working with even and odd functions, and they're good characteristics to know. Now a lot of trig functions have the characteristic of even or odd, usually more even than odd, but keep in mind that it's not over entire intervals, only over particular intervals. So let's go ahead and work some calculus problems, some integral problems, working with the idea of even and odd functions. Let's look at the integral from negative 2 to 2 of 4x cubed minus 3 dx. Now one thing I don't want you to get in your mind is just because, let's kind of roll back here a bit, just because I have an even power, notice here I had an even power in this function, Just because I have an even power doesn't make it an even function. You have to plug it in and double check that this characteristics holds true, because it depends on what else is going on with the function. Likewise down here, just because I have my odd number in my exponent, it doesn't make it an odd function. I have to go in and check. Now a lot of times in your homework set they're going to be saying, you know, integrate using the characteristics of an even or an odd function to find your solution. So sometimes they're telling you right away that it's symmetric. Okay, but I think it's a good idea to check. So let's go ahead and check this one out. This is not going to be an even function because I have the characteristic. I know if I plug a negative x in here, I'm going to get a negative x cubed out, so I know that's not going to work. So let's go ahead and check to see if this is an odd function. And of course you could graph these on your calculator very quickly and get a good visual idea of whether that's true or not. So again, if it's an odd function, f of negative x is equal to a negative f of x. F of negative x would be 4 negative x cubed minus 3. And we're checking to see if this is true. And then I have the negative of the entire function, 4x cubed minus 3. So this would be a negative 4x cubed, because negative x to the third is a negative x cubed times 4 is a negative 4x cubed minus 3. And then over here, I'm going to go ahead and distribute my negative and end up with a negative 4x cubed plus 3. Whoops, we better have a look at that. It doesn't look like they are equivalent, but let's run back and see if we have a negative sign or something running around that's incorrect. So I think this is not true. Okay, I've looked through my work real quick. So this is neither even nor odd. Now you don't even really need to check for this. You can just go ahead and integrate it and not worry about it. We could use symmetry in the fact that we could split up the integral from negative 2 to 2 of 4x cubed minus the integral from negative 2 to 2 of 3. That would be another option, but a lot of times when you're trying to figure out this even odd bit, it would have been easier just to integrate this in the first place. But this is how you could check for odd, and you can check for even pretty straightforward as well. So I'm just going to go ahead and integrate this. 4x to the fourth over 4, add 1, divide by the sum, minus 3x to the first over 1. And you don't have to put to the first over 1. That's just a quick way that we can verify the steps that we used to integrate. So when I get done simplifying, I get 4x to the fourth minus 3x, and I'm going to evaluate that from x equal negative 2 to x equal 2. And of course we want to put up our parentheses because I want to take my upper minus my lower. So when I plug in my upper, I'm going to have 4 2 to the fourth minus 3 times 2. And then down here I'll have 4 to the negative 2 to the fourth minus 3 times negative 2. Now I want you to be really careful to make sure, and I know I've said this several times, but it's a place that people often make a mistake. Make sure you always put these uppers and lowers in parentheses. Okay, simplifying 2 to the fourth is 16. 16 times 4 is 64, so I have 64 minus 6. And I'm going to go ahead and leave my parentheses up for my lower to make sure the negative sign distributes through. Negative 2 to the fourth would be positive 16 times 4 is 64, and then negative 3 times negative 2 is a positive 6. Now when I run this negative through, I end up with 64 minus 6 minus 64 minus 6. The 64's cancel and I'm left with negative 12. So what that's telling me that most of my area, if not all of my area, is below the x-axis. Now I'd like to go ahead and graph this, 4x cubed minus 3. So I'm going to go into y equal, clear this out, and again I encourage you to use your calculators to check your work, but you will only be given credit for the work that you show, not just a solution. So if I'm looking at this from negative 2 to 2, let me change my window just a bit. Expand that out. That doesn't look right. Window, oh there it is, negative 5, arrow down to 5. So I encourage you to make sure you check your work, but not just do your work on the calculator. So this is going negative 2 to positive 2. You can see that there's going to be a lot more bounded area down here. We can go to second calc and we can look at our integral option, and we can go lower limit negative 2, upper limit positive 2. and then it'll sketch this in for us. I might have to expand my graph a little bit because we can't actually see how low or how high this goes. So on the bottom end, gosh, when we were working, what did we have here? From the bottom end, let's go to 60 for my y min. Sorry, negative 60. And I just want to see that where it's bounded above and below. And I'm going to go top end at positive 60. Okay, it squishes the graph a lot, so it's not as easy to see the area, but now I can at least see my upper and lower bounded regions. Okay, so now I can see those shaded regions. Before it was kind of cutting them off, and I can definitely see that the area below is larger than the area above. And that's verifying for me then that the bounded area is equal to a negative 12. So again, I really encourage you again to use your calculators to check your work but not to do your work. Credit is given for work, not answers. Okay, so that's kind of showing what the area is that we're looking for. So this one didn't have the even odd that I could use, but I could use some of the ideas from my previous sections of using the power rule and integrating from there. I could have also split this up into two separate integrals to work with that as well. So the idea of symmetry, when we're talking about splitting the limits of integration, let's say from negative 1 to 1, I could split them from negative 1 to 0 and then 0 to 1. I just can't double the integral unless you're being very careful about whether you have an even or an odd function you're working with. So my take on this a lot of times is by the time you get done doing all that work rewriting everything, you could have had the integral done. So I don't necessarily rely on that so much, but if you like those particular characteristics of integrals, you absolutely can. Okay, another integral. I could take this negative 1 to 1 and I could split it up, negative 1 to 0 and then 0 to 1, and then I could look at each piece and say, okay, is that an even or an odd function, and then use those characteristics. But again, I think it takes less time just to integrate it. So let's go ahead and integrate. The integral of 1 is x. The integral of x is x squared over 2. Integral of x squared is x cubed over 3. The integral of x cubed is x to the 4th over 4. Nothing cancels, nothing simplifies, so I'm just going to go ahead and evaluate this. Again, I always want to put up my upper minus my lower in parentheses. Plugging in a 1, I get 1 plus 1/2 plus 1/3 plus 1/4. And then for my lower, let's see, plugging in a negative 1, I have a negative 1 plus 1/2 minus 1/3 plus 1/4. Okay, now why are my signs changing? Remember, if I have a negative to an even power, it's positive. If I have a negative to an odd power, it's negative. So simplifying, I have 1 plus 1/2 plus 1/3 plus 1/4. I'm going to take the negative and distribute it. So I have a plus 1 minus 1/2 plus 1/3 minus 1/4. So one of the reasons I didn't find our common denominator right away is I was kind of hoping some things would cancel, and some things do. So the halves cancel and the fourths cancel. So what I'm left with here is 1 plus 1 is 2. 2 plus 1/3 is going to be 2 plus 2/3, which would be 6 plus 2 over 3 8/3. Now we don't like mixed numbers, we like our improper fractions, so make sure you think about things in improper fraction form. If you had switched this to a mixed number at this point, just make sure you convert it back to an improper fraction before you input your solution. Now we can also work with trig functions, and I love trig functions, so let's have a look. Let's look at the integral from negative pi over 2 to positive pi over 2, and let's use 6 sine of x. Now here I'm going to make sure I know my antiderivatives. Now if you want to, you could split this up from negative pi over 2 to 0 and 0 to pi over 2 and integrate separately. But again, by the time you do all that, to me it's easier just to integrate it straightforward. So I'm going to pull the 6 out, and I want to think about the antiderivative of the sine of x dx. Now the derivative of cosine is sine. Oh, it's negative sine. So the derivative of cosine is negative sine. So the integral of sine should be a negative cosine. So this is a negative 6 cosine of x evaluated from x equal negative pi over 2 to x equal positive pi over 2. Now with the negative 6, I can drag it through if I want, or I can just pull it out front and then worry about my upper and lowers. Doesn't matter. Either way works. So plugging in my pi over 2, and I have my negative 6 out front, so I don't need to worry about including that. I kind of like to pull coefficients out front because it gives me less to keep track of. And then for my lower, I have cosine of negative pi over 2. Dragging along the negative 6, put up my brackets. The cosine of pi over 2 is 0. And over here, the cosine of negative pi over 2 is also 0. So 6 times 0 is definitely 0. So what that's telling me, it doesn't say that there's no bounded area. What that's telling me is probably the area above and below the x-axis is the same. We can graph this real quick to check. So let's graph 6 sine of x. And again, you can evaluate this directly from the other screen, but I like to look at the graphs. And this is from negative pi over 2 to pi over 2. But let me go ahead and put in my graph first. So negative pi over 2 would be about negative 3/2. So let's go to negative 2 to 2. And then negative 60 to positive 60 seems like quite a bit of overkill. I'm going to go negative 10 to 10 because this graph is stretched by a factor of 6. There you go. So negative pi over 2 to pi over 2 is somewhere right in here. These are in radians, but they're not in multiples of pi type of radians. So now we can go to second calc. And we're going to integrate this. And my lower bound is negative pi over 2. And then my upper bound is positive pi over 2. Maybe I should have hit enter. Let me try that again. Second calc. Going to integrate. So negative pi over 2. And then my lower integral, my upper limit of integration would be a positive pi over 2. Hit enter. Now it'll shade it in. So you see this area above and the area below, they're exactly the same. And so they can end up canceling each other out. And so the sum, or the total area, the total net area, is 0. Okay, so again, it doesn't mean there's no bounded area. It just means the area above and the area below are the same. But that's the integral. That's what I'm trying to find. And so my value is 0. Now, if you wanted to talk about other things like total area, then that would be a whole separate problem. So when you're looking at these, you have to be aware of like getting an answer like 0. It doesn't mean there's no area, it just means there's no net area. Now there's other things that we can do with integrals. We've looked at quite a few right now so far with integrals that we've been able to integrate straightforward. But what about something that I can't really work with straightforward? I don't really have any rules yet to integrate negative 10 to 10, and my function would be x over the square root of 190 minus x squared dx. Now this one pops up in your homework selection, and I don't really think at this point we're actually ready to integrate something like that. So we kind of have to think about what's going on with this type of problem and maybe apply some rules that we haven't learned yet. So we might learn a couple new rules here. Now this doesn't allow me to apply the power rule, and we don't know U substitution yet. So those of you who have been exposed to U substitution before, you could definitely use U sub on this. Those of you who haven't seen that yet, we're going to be learning that fairly soon. But what we can do here is we can look at this function and we can say, you know what, I can't use the power rule. That's the only thing I know how to do right now with integrals. What else could I use? Well, let's look at this in terms of whether this is an even function or an odd function. I think if anything it's going to be an odd function. Just from experience, I can look at this and think, well, this is going to be the same no matter what I plug in, because a negative squared will always be a positive, but the numerator could change. So if you remember, with an odd function, f of negative x is equal to negative f of x. So let's go ahead and check this out. F of negative x, that would mean a negative x over the square root of 190 minus negative x quantity squared. and I'm checking to see is this true, and then I'm going to negate the entire function. And we're going to see if these are equivalent. So over here on the left, I get a negative x over the square root of 190 minus x squared. And again, negative x times negative x is a positive x squared. And then we can see over here on the right, this negative only really distributes to the top. It doesn't go to both top and bottom, so these are equal. So this is an odd function. And because it's an odd function, I know that this integral is equal to 0 without even having to integrate it. Plus, I can't integrate it. It's not a talent that I have yet. It's not a skill that I have yet. So let's go ahead and open up our calculator and let's integrate this one. Again, you don't have to always graph it. I like to graph it because I like to see the visual of what's going on. You could also use this screen to integrate it straightforward to check your work. I'm going to go ahead and graph it though. Now, when you're graphing, if you don't have this nice little fraction key, just make sure you use the correct fraction bar and the parentheses to demonstrate exactly what your numerator and denominator are. So let's go ahead and graph this. We're going to definitely have to change our limits of integration. This looks like a flat line, but it's definitely not. This needs to go from negative 10 to 10. And then my y min and y max, I'm going to go something like negative 2 to 2. I just want to kind of get an idea of what's going on here. Now it doesn't look like a flat line. Now if I integrate this from negative 10 to 10, I can see that the area above and the area below are the same, so positive and negative will cancel each other out. But let's go ahead and double check it. So again, lower limit is negative 10, upper limit is positive 10. And then the shaded region, this is all negative area because it's below the x-axis. This area over here to the right is going to be shaded area that's positive because it's above the y-axis, and they end up canceling each other out. Okay, so we can see that the overall integral is equal to 0 there. And again, we didn't actually have to integrate to even find that. In fact, given what we have learned so far in Calc 1, I couldn't integrate it. I have to learn a few more techniques of integration before I could actually integrate this. So you'll run into some different types of problems where, for now, I have to use that idea of even odd in order for me to figure out what's going on. Next thing we want to look at is the average value of a function. Now we know how to find the average value of a data set. You add up all the values and divide through by the total number of values. That's just finding the average. But now we want to look at the average value of an entire function. And this is harder to do because there's an infinite number of values in a function. So what we're going to think about for the average value of a function is the same type of thing. But instead of dividing by the total number of values, we're going to divide by the total width of the function. So in a notation that this particular textbook uses is f bar. This means average of f. So the average of f is equal to 1 over b minus a. This is the width of the interval, so I'm dividing by the width of the interval. And then here I'm basically summing up the rectangles from a to b of f of x dx. So this is the average value of a function. This is definitely a formula that you'll want to know. And at some point we're going to use this, and we're going to be talking about another interesting characteristic that we can do to find the exact value of c that provides the average value of the function. But first, let's go and look at the average value of a function. Let's go ahead and look at an example, and we'll also look at this graphically about finding the average value of a function. So let's go ahead and find the average value of the function. Let's do something a little different, not just a polynomial. Let's do f of x equals 1 over the square root of 2x, and let's do this on the interval from 1 to 25. Okay, so we want to look at this graphically, and then we also want to find the actual average value. So graphically, this is going to look like the graph of 1 over root x as a parent graph, And then of course there's going to be this factor of root 2 that I need to involve as well. But basically I'm looking in the first quadrant because my x values have to be positive, because I can only take the square root of positive numbers when we're working with the real number system. So I could plug in some values here. I can't plug in a 0. Let's start at 1. So if I plug in 1, I have 1 over the square root of 2. And that 1 over the square root of 2, that's going to be somewhere, let's say, up in here. And then I can keep plugging in values, and as my values of x get larger and larger, my values of f of x get smaller and smaller because they're in the denominator. So let's say this is from 1 and this is to 25. So I'm trying to find the average value here. Well, the highest value is whatever this was. That was 1 over the square root of 2, I believe. And over here at 25, the lowest value would be 1 over root 50. So somewhere in between is that average value. And so that's what we're trying to find, is this value of f bar. Is it weighted more toward this end or more toward this end? And that's what I'm trying to figure out. And usually, when you're trying to guess that average value, let me get those back in here. There. When you're trying to guess these average value, the best thing you can do pictorially is only take a guess between the minimum and the maximum value, but it's somewhere in here. Okay, and so we'll maybe call this f bar. This is my guess. Well, to find f bar, we integrate. Actually, let's do our 1 over b minus a. Well, I'll write out the formula first. And I integrate from a to b. Of this case, 1 over, just f of x dx, and then I'll write the specific. So specifically, this would be f bar equals 1 over b minus a, so that's 25 minus 1, integral from 1 to 25 of 1 over the square root of 2x dx. So it's going to be important, again, that we'd be able to integrate. It's a good skill to have. So f bar would equal 1 over 24, integral from 1 to 25. Now this 1 over root 2x, I can rewrite that as 1 over root 2 times 1 over root x. And then, and again I'm just rewriting this, I still haven't integrated it, I can pull that out front. So that's going to be 1 over 24 root 2, integral from 1 to 25 of 1 over root x dx. Now I'm going to flip this up top so I can use the power rule. So now I'm finally ready to integrate this. Okay, so again, haven't integrated yet, but now we will do that. So I'm going to drag along the 1 over 24 root 2. We're going to add 1, because it's a negative 1/2 right now, divide by the sum. When you divide by this fraction, you multiply by the reciprocal, so it's going to pop up top. So this 1/2 is the same as multiplying by 2 over 1, so I'm going to pull the 2 up over here, and this would be x to the 1/2 then. Or if we wanted to think about it, we could just look at it as square root of x. Now I can simplify this a bit. 2 goes into 24 12 times. So this is 1 over 12 root 2 root x evaluated from x equal 1 to x equal 25. This is a coefficient, and I'm just going to pull it out front, and then I'm going to evaluate my variable component. So that would be root 25 minus root 1, always upper minus lower. So square root of 25 is 5, square root of 1 is 1, 5 minus 1 is 4. So I'm left with 4 over 12 root 2, and of course 4 goes into 12 3 times. So this looks like 1 over 3 root 2. That is not my area, that's the average value of my function. So, kind of running out of room here. That's telling me that f bar is 1 over 3 root 2. Now, on a calculator, let's figure out what this is, just to double check our work. So I'm going to look at the graph, and that's going to be 1 over root 2x Now we might have to change our scale here, I think we could just go 0 to 1 on our y-axis, and I think that's going to help us kind of zoom in quite a bit, because we don't want the graph to look flat. There we are. Now on our y-axis, we want to go clear out to 25. So let's go 0 to 25 on our x. Okay, so we're trying to find the average value of our function here. Now 1 to 25 is the region that we're looking at. And we thought the average value of our function is this 1 over 3 root 2. So let's go ahead and graph that as well. So that's going to go on my next line. And again, that's going to be 1 over 3 root 2. Now I'll have both these. So this is the average value of the function. And it looks pretty reasonable. I can't see from this picture that that's correct, but it does look reasonable. Now, if I want to find the integral of what I have over here, I can't just necessarily graph that directly because I have this 1 over 24 out front that I need to work with. So for this one, let's go ahead and pop into just your regular screen. Let's go into, whoops, you might not be able to see this. There. Let's go into our regular screen and go into Math. I'm choosing my option of integration. But out front of that, I want to put in, let's see if I have that right. Yep, 1 over 24 out front. And I'm going to integrate this from 1 to 25, because remember the 1 over 24 came from 1 over 25 minus 1, and this would be 1 over 2 root x, or sorry, root 2x. Get back to that denominator here. Okay, 2x, and then of course my width is that incremental width of x, so this is a dx. So when I integrate this, it's probably not going to give me that 1 over 3 root 2 like I'm expecting. It's going to give me a decimal approximation. So I need to convert that. So we'd go to Math, Frac. You know what? That's not even going to work because it's just going to give me a fraction if it converts it at all. Let's do this instead. Let's just go 1 over 3 root 2 to get our decimal approximation from our solution and see if they match. And they match, and so that tells me that I have the correct answer. Now, on a test, a quiz, a handwritten homework, this is not an acceptable answer. This is a way to check your answers. Our answer we want is this 1 over 3 root 2. So make sure that you are showing all of your work in order to receive credit. This will receive nothing. It's just a way to check your work. So that's an example of finding the average value of a function. Now you can do this with trig functions. You can do this with all sorts of other types of functions as well. One thing that has to be true though is it does have to be defined just as anything would have to be in order to be integrated. Now when you're trying to find the average value of a function, sometimes you'll be given a generic value, let's say like x to the n, and you can still work through that. It's a little more complicated, but your integration skills are there and so are your algebra skills. So go ahead and give those a try, even though they look a little more difficult. Just go through the process and pretty soon you'll start to see an algebraic equation fall off that you'll be able to solve. Now one of the things that this is leading toward is a very exciting theorem. It's called the mean value theorem for integrals. Now we've looked at the mean value theorem before. But now we're going to look at the mean value theorem for integrals. Well, what the mean value theorem for integrals says, there has to be some value of c on the interval where I find this average value that will give me the exact height of that average value. So when we're looking at this, and I think in your book they use t's here, it doesn't end up mattering. So when we're looking at this picture, up here, this explains it pretty clear. I'm looking for this value of c that will give me this exact height. So the mean value theorem says I want to know what value it is from 1 to 25 that I can plug in and get the average value of the entire function back. So that's what the mean value theorem for integrals tells us. And it's a pretty slick little deal. And of course, algebra is going to come into play here big time. So let's go ahead and look at the value of c. We want to find the value of c for the function. Let's do a trig function. So find c from the mean value theorem. Let's use that trig function f of x equals cosine of x. And let's do negative pi over 2 to pi over 2. Okay, so let's go ahead and set this up. So first part, I'm going to use the average value of the function. So I'm going to find f bar. So f bar is 1 over pi over 2 minus a negative pi over 2, 1 over b minus a, integral from negative to positive pi over 2 of the cosine of x dx. So that's my first part. So this is part 1. Okay, so this means f bar is equal to, so pi over 2 minus a negative pi over 2 is a plus pi over 2. Pi over 2 plus pi over 2 is 1 over pi. Now if I look at the integral of the cosine, the integral of cosine is sine. The derivative of cosine is negative sine, but the integral of cosine is positive sine. And again, that's just for knowing your antiderivatives. And I want to evaluate this from x equal negative pi over 2 to x equal positive pi over 2. So this is 1 over pi sine of pi over 2 minus the sine of a negative pi over 2. Sine of pi over 2 is 1 minus, because I'm subtracting, the sine of negative pi over 2 is a negative 1. So this is 2 over pi. So this is equal to f bar. So what I'm trying to find here then is f of c equals 2 over pi. Where is this true? Well, let's figure out what f of c is. F of c is the cosine of c, because that's my original given function, equals 2 over pi. Now this is not going to be a pretty solution, but we can definitely find where this is occurring by taking the inverse cosine of both sides. So we're going to need a little calculator help for this. If this would show up on a handwritten homework or a test, these would be values of the unit circle that you would know. You wouldn't have to use your inverse trig functions on your calculator to figure this out. So if we grab our calculator, we're looking for the inverse cosine, so inverse cosine of 2 over pi. Whoops. Try that again. For some reason I keep jumping into my y equal. So the inverse cosine of 2 over pi. Now this will be a decimal approximation, but this is in radians. And again, on a test or a handwritten homework, these would be values that you would know from the unit circle. But for this one, we can use our calculators to approximate that inverse trig function, because this is not something I would expect that you would know off the top of your head. So this tells me that this is the value of c is approximately equal to, we better use approximately equal to 0.881. So this is the value of c guaranteed by the mean value theorem. So graphically, let's see what this looks like, because I'm kind of, this isn't really clear to me what we just did. We found c, but I'd like to see a picture of what's going on. We need the graph of cosine of x from negative to positive pi over 2. So let's go ahead and look at the graph of the cosine of x. And then we'll adjust our window from negative to positive pi over 2. That's definitely not a good graph so far. So my x min, let's go negative pi over 2. And my x max, let's go positive pi over 2. And of course we know with a trig function that hasn't been transformed for cosine, we should be able to go negative 1 to 1 just fine. So this right here is the picture I'm looking at, and I'm trying to find the average value. We think that that average value is going to be 2 over pi. So we think the average value is 2 over pi. So let's go ahead and plug that in. And I'm drawing the line 2 over pi. That's what we're up to here. So this is the average value. Now it's saying, what could I plug in to find that average value? Well, if we look at this, it looks like we could plug in, if I come straight down here to my x-axis, something right before the number 1. And if I look over here, it's something right before the number -1. So I found one of my solutions, but I didn't find all of them. That's kind of what this is saying. So this point right here, I could find this on my calculator using the intersect function, but I just want a picture of what this looks like. And it verifies what I think is going on, and that's kind of what I wanted to get out of this. So let's go ahead and graph this. So the blue graph, this is f of x equal cosine of x. Okay, and this is equal to 1, and this is equal to a -1 on my axis. Now this red line right here, this is equal to f of c is 2 over pi. So this is f of c equal 2 over pi. This is the average value of my function. Now the question is, find the value of c that makes this true. Well, the value of c that would hit this spot would be right before here. So this is the value of c that makes that true, and it's approximately equal to 0.881. So that's what I'm looking for, is I'm looking for the value of c on the interval that makes that true. Now sometimes there's restrictions on your solutions. They might say find all the positive values of c that makes that true, and then we would have that. But I also think there's another negative value right here. I want to pop that in as well. And I think that this, due to symmetry, would be the -0.881. But I'm just going to be looking for the positive solution right now. So again, if you want to find the other solution, you can, but just make sure it's actually being asked for in the problem. So some of the homework problems you'll run into, you're not going to be given a specific function. They'll just be giving you these summary values. But again, you can run through your algebra pretty easily to try and come up with those solutions. As usual, if you have questions, please let me know. I'm happy to help. You can also use Pearson Connect, or you can contact me via text and we can set up an appointment to meet online with any questions that you might have as well. Good luck.